So in this lecture, we have seen how to obtain the sampling distribution of sample mean, and we have also visualized your central limit theorem. Now we are going to move on to the sample variance. So we will be looking at the sampling distribution of sample variance. So we need some important libraries for this. So let me just import all of them once again. Import pandas as PD, import numpy as NP. So you all know that what are the roles of these different libraries. We have been using them since the first week. matplotlib.pyplot as PLT, and then from this scipy stats module we will be importing from scipy.stats import chi-square comma norm. So this chi2 basically means that we will be working with chi-square distribution, and this is your normal distribution, right? So these are the two functions from scipy library that we would be using it, because you know that when we are talking about sample variance, then chi-square distribution would come into the picture. So now let us reload this data set. So for loading the data set, suppose you use this. So we will use the pandas library read underscore CSV function over here, and we will write the name of the data set ODT underscore perception underscore data dot CSV. Now same way as we have done earlier, we would be defining the sample size and also the number of samples that we will be drawing from that data set. So let us first see sample size. Suppose you want 140, the size of each sample would be 140, and how many samples do you want? Let us write it as 1000. So it will be drawing 1000 samples, and each sample would be of size 140. Now we would create an empty list to store the sample variances, because in each iteration it would be calculating the sample variance and then it will be saving in your sample variances in a list. So for that we will initially create an empty list, and then we would keep it updating. So first of all, we will create an empty list. Create an empty list. So here we would write, so sample underscore variances. So this was create an empty list called sample variances to store the sample variances calculated in each iteration. So now we would basically initiate a for loop, and in each iteration it would take a sample from that age column, and that would be of size 140. It would calculate the variance of that, and then it will add it to this sample variances list. So let me write that for loop. For I in range. So as I have explained you the roles of these terms over here, num samples, and then we would be drawing a sample. Sample is from this data frame. We would be taking a random sample of sample size that is 140, and then sample variance basically would store your sample. From this we would be focusing suppose on age column. For that we would calculate your variance. So sample variance, you have calculated the variance of that sample. Next we would append it to the list. So sample variances. So the list originally the name is sample variances. So you will dot append basically, and here you will write the sample variance that you have calculated just now. Fine. So you have initiated a for loop over here, and it will keep on calculating, taking a sample of size 140, calculates its variance and add it to this list, and this will go on for 1000 samples. Now, in order to plot the histogram, we need to find the range of the sample variances. So for that, we would calculate the minimum and the maximum of this. Minimum sample variances, this would be min of sample variances, and max underscore sample variances, max of sample variances. So this would calculate your minimum and the maximum values of this sample variances list that you have already obtained after this for loop has ended. Once you have that, it would help you in determining the x-axis of the histogram. So now we are ready to plot your histogram. So PLT, we will use this hist, and here we want to plot sample variances, so that we will write first. Next, we will specify the number of bins, suppose it is 20, and the range basically would be from minimum to the maximum. So let me just copy it as it is from here, and here it would be maximum. The range has been specified. Now we would specify the density as true. So if you can recall, it is used to normalize your histogram such that the area within those bars below that curve would be 1. Now, so in order to have some transparency to the bars, we can have alpha as 0.6, and finally if you want to label it, we can write, suppose, sample variance distribution. Label alpha is this, and sample variance, so label, it should have one more. So if we run it, let us see what do we get. So this is what you get. This is the histogram you obtain when you run these codes. Suppose you want to overlay a chi-square and a normal distribution on this. So what should be done in this case? So if you want to overlay a normal distribution curve, so let us see. So in this code itself, we can write over here at the end. So now we will continue from here. If you are trying to overlay your normal distribution curve, so it means that you need to find the mean and the standard deviation of that first of all. So we would calculate mean underscore sample variances, because this is what contains all the sample variances. So you will use numpy's mean function, and here you would write sample variances. So this would give you the mean. Similarly, std underscore sample variances, and again if you use the numpy libraries std, so that would give you the standard deviation. Now we will define the range of values for your distribution. So let us say that x, we are going to create, x would be your array basically, and it will create the values for the x-axis, okay, or you can say the range of sample variances, and we will also have the corresponding values for your y-axis. So first of all, let us write x as np.lin space, space. Basically it is a numpy function that generates evenly spaced values over a specified range. So here we are giving this range as from minimum sample variances to the maximum, okay. So here let us use that. Minimum of this minimum sample variances, and here the next would be maximum of this. Also we would specify that there should be 1000 points between, evenly spaced points between these two endpoints. Okay, so this line would basically create an array X that would basically be the range of X values for this normal distribution curve. Now you can generate the values for normal distribution curve. So that would be y underscore normal, suppose, because we will be needing for chi-square, so we are adding this suffix normal. So here we would use norm function, norm dot pdf. X is the input that we will obtain from here, and we will specify the LOC, that is the location. It would be set to mean of sample variances here that we have obtained, and we would specify the scale also as this one, standard STD sample variance. Okay, after this you are ready to plot your normal distribution curve. So for this we will use your matplotlib plt.plot x comma y normal would be there, and for this suppose you use green dashed line and you want to label it as normal distribution, normal distribution. So let us run this and see what do you get. Okay, so you see that now in addition to your histogram, you have now overlaid a normal distribution curve on this. Now in the same way one could also overlay your chi-square distribution, because that is what we are interested in, because sample variances would be distributed n-1 times s square over sigma square. That follows chi-square distribution with n-1 degrees of freedom. So for plotting your chi-square distribution, you need to first specify the degrees of freedom. So let us define the DOF, that is degrees of freedom, as whatever is the sample size, that would -1. Next you would specify the range of X values. So NP NumPy libraries linspace function over here, and the range is 0 to 200 suppose, and 1000 are the data points that we are interested. After this you can generate the value. So this is for the X axis. For the Y axis we would be having, suppose we just write PDF, this would be chi2, because this is the function that we have initially called from your SciPy library. So from this, so earlier you see we use norm.pdf, here it will be chi2, that is chi-square.pdf, and here X would be there that you have obtained in this line, and then for chi-square you need to specify the degrees of freedom. So degrees of freedom would be sample size -1. Next you can finally plot it, plt.plot X would be there, PDF would be there. This is what you have obtained. Maybe we could just write y underscore chi, and here it would be y underscore chi, and label would be, and we can use the chi, this f string over here. So degrees of freedom would be evaluated and then substituted in this case. So is equal to DOF chi2 is not defined, it is saying, so we have already used it over here. So let me just restart and run all the cells. So you see that it shifts to this left hand side. So as the degrees of freedom increases, as basically you are taking a larger and larger sample, it is giving you a proper fit towards your normal distribution. Now you can basically customize this and beautify it if by adding the sample size over here, or you can add the legend over here. So all those things can be done. So for this we will use the plot.annotate function, plt.annotate. okay, so here we would write f sample size. Suppose you want the sample size coming in this way, so you would just write sample size. Then we would specify the position of this. So xy suppose is 0.7, 0.9. These are the coordinates, and we also want the xy coordinates as x's fraction, as I have explained these earlier also, and you want the font size as 10. So this would basically annotate the plot to display the sample size information also. Okay, so sample size 100 is also coming. So let me just go back and write it as 140, the original one. And maybe for here the green color could be changed to red so that it is more visible to us. So here I want 140 also to be red. This one has to be redone. So you see that this red color, blue was the original histogram that we had, and this red color was the normal distribution curve that we fitted, and this orange color is your chi-square distribution. Okay, and we have displayed the sample size information also on top. You can change this position by changing these coordinates over here. Now you can see that it is going from minimum to your maximum sample variance, basically min and max that you have calculated over here. So if you can see what is your minimum sample variance, so variation, it's starting from 109, and what is the maximum? $166.57. So it's going somewhere here. Okay, so chi-square, see that we have written for x values, when we were plotting chi-square, we wrote that it should start from 0 to 200 and there should be these many number of points. So 0 is starting from 0 and it is going up till 200. Now if you further want to make it better, you can add the x label and the y labels. So we can have plt.x label. So we would write as sample variance, and your y label could be densities. You can also add the title to this plot. It will be sampling distribution of the sample variance, sampling distribution of sample variance. And we can also set the x-axis limit to show the entire range. So for this we can just write plt.x limit. It would go from 0 to the max of your sample variance. So we just do not want it to go over and above that. Okay, maximum, let me see what we have used the term, max sample variances. Okay, fine. And next we will use plt.show to display whatever we have defined. Okay, so now yes, said that the x limit should not go beyond the maximum of the sample variances, and as we have calculated, the maximum is 166.5, so it will go, it is displaying only till that end. So this is how you can find out the sampling distribution of sample variance. Now the last topic for this week is the sampling distribution of sample proportion. Proportion, if you can recall, it is p hat was x by n, where x was your binomial distribution. And we said that it can be approximated using the normal distribution, and we saw one example also for that. So now let us see if we have to do that in Python, how do we do it? So for this we need some libraries. So we already have NumPy, Pandas and Matplotlib. From SciPy we need binom function now, and here instead of chi-square, and no, I can just write norm comma binom. Okay, so this will be used for binomial distribution. Data frame we have already defined earlier, so let me just use it over here so as to make it more fresh. Sample size, again we can define, suppose sample size is 10 in this case, sorry, sample size, and the number of samples would be 1000. So it would draw 1000 samples of size 10 each time from your column. Suppose you are interested to see the proportion of excellent content quality in overall case. So because if you remember, the content quality had different categories, and suppose it was, in that case, it was content quality basically can be excellent, it can be good, poor, and I think there are one more category. So 4 categories were there. So, and in this case you want to see the proportion of excellent who have marked excellent. So now for this we will again create an empty list. So let me just write sample underscore prop. I would write for this a simple word. Okay, so this would create an empty list, and it will store the sample proportions that will be calculated in each iteration. Now, as we have done earlier also, we will initiate a for loop. So maybe I should write all these in the same input, then it is better. For I in range would be num underscore samples, and here we would be drawing a sample, random sample. So sample df dot sample underscore size. Okay, so from this data frame you would be taking a sample of size 10, and from there you would be calculating the sample proportion. Sample prop 1 I am using because prop I have already used. Sample prop 1 is equal to, in the sample you would compare content quality okay, if this is excellent, then you would calculate the mean for those particular rows from there. Okay, so here you are calculating the proportion of excellent content quality. Okay, so it would calculate, basically it would count the number of excellent values in that sample, and it would divide by the total sample size. Okay, so, and finally here it would be appended in your sample underscore prop dot append your sample prop 1. Okay, so this has basically initiated a for loop, and every time it will take out a sample, check the proportion of those who have marked excellent. For that it will find the proportion, and then after finding that out it will add it to this empty list over here, and it will get updated, and this process will be repeated 1000 times. Now if you are ready with these sample proportions and you want to plot the histogram, So for this again we need the x-axis values, and for that we need the minimum of the sample proportions, minimum underscore sample prop. This would nothing be but minimum of this sample prop that we have saved over here, and the maximum underscore sample prop would be maximum of this. And now we are ready to plot your histogram. So we can write plt dot hist. Okay, we would be plotting this, okay, sample proportion. So we can just copy here, number of bins would be 20, range would be from minimum sample prop to maximum. Again, here the density would be true because we want to normalize it. Density is equal to true, comma. So alpha, again same steps are there. So instead of just the sample mean or the sample variances, you are replacing it with the sample proportion, and you can label it as sample proportion distribution. Okay, let us see what it is showing. So sample, it should be sample over here. So this is how your histogram would look like. Since this is your proportion, is a categorical variable, so it is appearing in this way. Okay, so you have plotted it. Now if you want to fit a normal distribution over this for comparison, so we can do that. Again, for that we need to calculate the mean, variance, and then we would find out the x values, corresponding y values, and fit your normal distribution. Okay, so let us first find mean underscore sample underscore prop. Okay, so this one would be NP, so you would use the NumPy libraries mean function, and here you will just write the sample prop that we have written here. Right, next one would be std underscore sample proportion. This would be again solved using this function from this NumPy library. Now you can generate the x values and the y values. So x would be np dot nspace. So for this you need to specify the range, so it would go from the minimum to the maximum. So we can just use this minimum to the maximum, it will go. And how many points do we need in between? We can take suppose 100 points, 100 equidistant points, and the corresponding y values would be found using this norm.pdf. Okay, so x would be the input and location, that is LOC, would be the mean that we have obtained over here, and your scale would be the STD that you have obtained here. Okay, now finally you can plot it. So x would be there, y, and if you want to display it using r dashed line, it would be this, and then you would write the label as normal distribution. Okay, you can see that it's giving you so beautifully over here. Okay, and further if you want to display the sample size also, you can add that annotate function Okay, you can add the x-axis label for this, label for y, so we can just simply use that from here. So x label would be sample proportion corresponding to your content quality. Here this would be density, this will be sampling distribution of sample proportion, and here we want the legends to be present. Legend should be visible, and plot dot show. Okay, so the normal distribution, this is coming in, this is the legend, right? So normal distribution, sample proportion, blue is your sample proportion, that is the histograms that we have drawn, and we have fitted the normal distribution on this. So you can see that in the theory we have studied that your binomial can be approximated by the normal distribution provided np and n into 1 minus p, that is nq, is greater than or equal to 10. In some books you would find that it is, instead of 10 you use the value 5. So if np is greater than 5 or n1 minus p is greater than 5. So that is the threshold value. So you have to fix on 1 and then use it throughout. Okay, so this is all about your 4th week, which is on sampling distribution. So we have seen sampling distribution of sample mean, sample variance and sample proportion for a single sample problem, and we have also visualized your central limit theorem. So in the next week we would talk about the sampling distribution in case of 2 sample problems.